Guys, today we are back with another problem. Before I go and deep dive into the problem, make sure you guys like, share and subscribe to the channel. And today's problem is on dynamic programming, and today's particular problem statement is that we have to find the minimum cost of jumping from one stone to another. So this is one of those similar problems which we have encountered in minimum frog jump. So if the problem statement tells that it's a minimum frog jump, you are going to apply the same logic. It can be also the minimum number of cost required to jump the stairs. So I can also say jump problem, stairs jump problem, okay, and also a stone jump problem, and that's how we have to solve this particular problem. So let us read the particular problem statement. It is saying that we have to find the minimum cost of jumping from one stone to another. Okay, fine. So what it is saying that let us first understand this with the help of this diagram. So what we can see is this is a stone, okay, and the stone is having a particular height. Every particular stones are numbered from 1 to 5. So what you can see, this is stone number 1, this is stone number 2, this is stone number 3, this is stone number 4, and this is stone number 5. Each stones have particular height. This particular stone is of the height 10, then the second stone is of height 30, then the third stone is of height 40, and the last stone is of height 50, and the extreme last is the height 20. Okay, so what you can see is that the particular person can jump the stones with the number of jumps permitted as k. So what I can say, k in this case is 3. Okay, why 3? This is given as input. Okay, so what is the path in which the person can jump from the first stone to the last stone? Remember one thing, you have to go from first stone to the last stone. Okay, over here 20 is my end, okay, and 10 is my starting stone. 10 is my starting stone. So what I am doing particularly over here is I'm going from my starting stone till my ending stone, which is 20. Okay, in between I will be encountering stones of various sizes, and each size represents particular heights and some cost as well. Okay, so what we are seeing is if the stone particularly travels, if the person particularly travels from 1, 2 and 5, that means from 1 to 2, it can take a maximum number of jump. Remember one thing, that the maximum allowed jump is 3, means it can skip 3 stones at max, after which it can't do anything. Okay, so what you can see is from 1 to 2, it is taking a pathway as 30 to 20. So we can take the absolute difference of 30 and 20, 30 and 10, so which is giving us a 20. Okay, similarly from path 2 to path 5. So if you have to, suppose you want to go from path 2 to path 3, and again from 3 to 4, then 4 to 5, then you just do this summation. This value will never be a minimum value. It will become 30 plus 10, 40 plus 40, 80, and then 50. This value further goes increasing. That means our cost is not optimized. We have to travel in such a way that we require very less possible cost. That's the reason we are going to use dynamic programming. Whenever the word dynamic programming comes, remember, we have to remember all possible ways. All possible ways. Now this can be solved with the help of a recursion and tabulation method as well, but I'm not solving it because dynamic programming helps us reduce the number of overlapping subsequent problems, and it is the most optimized solution possible. Okay, so what we can see over here, from 1 to 2, we are taking the absolute difference of 10 to 30, which is coming as 20. From 2 to 5, that means from the second I'm giving a jump till 5, that means I'm taking 3 jumps, 1, 2 and 3. And why I can take 3 jumps? Because my maximum value in which I can jump is 3. I can also take 2 jumps, but in that case again from 3 to 5 I have to take another 50. That means my path is not optimized. So in this manner I can get the optimized path as 2 to 5, means from this particular direction, which is 30 to 20, I am getting 30 minus 20 as 10. Now if I add the previous path with this particular path, what I'll get, the total cost as 30. You can try out other combinations in which you can jump from one stone to another. You will still see that 30 is the lowest possible number, and we have to find this lowest possible number or the minimum cost required. Okay, so let us first see. Okay, so what we can see, that we will be given an array. So in the question, obviously you won't see stones, right? The question will be very simple. The question will have indices. So these 0, 1, 2 and 3, 4 are the indices of the array. 10, 30, 40, 50 and 20 are nothing but the heights of each stones present inside the array. Array represent the height of the stone starting from the first stone and can jump up to k stones. So that means I can jump from here to here, I can jump from here to here as well, I can jump from here to here, I can jump from here to here max, because k is 3 in this case. K is 3 in this case because it's seen in the input statement. If you open the GFG, if you see, k is 3. Okay, so what if I have a value as k equals to 1? That means I can only take one consecutive jumps. I can never jump two jumps. Okay. In that case, my output will be large. Okay. Since we have a liberty of k as 3, that means we have a higher jump probability. That means we can reduce down the cost. So remember one thing, whenever k will be large or 3 or 4 or large values, and the size of the array is small, that means what we can conclude? We can conclude that the cost will be also small. So it's like you have a bigger plane which can cover a small amount of distance. That means obviously you have to optimize the cost. Okay, like that. So what you can see is the cost of jumping from stone I. So imagine there are two pointers. So imagine this is pointer A and this is pointer J. Okay, pointer A and J. So what I can write is, let me just clean this mess. Yeah. So what I can write is, if I have two pointers, I and J, I have to go till J and J have to go till the next I, and the cycle continues. But we have to find the cost. So the cost can be calculated by taking the absolute value of the element present at the index I minus the element present at the index J. From first position of the first stone, this is the first stone, till J means the stone next, the next stone which we are going to overcome. Okay. What is our goal? Our goal is to minimize the total cost, as I already told you, to reach the last stone. This is the last stone. From here to here we have to reach, and we have to find the minimum cost in order to reach this last stone. Okay. Now let us analyze the algorithm. So what we will be seeing is, we will be having a DP table which will keep track of the minimum cost to reach each particular stone. So each particular stone will have a track. So you know that from stone 1 to stone 2, I am keeping track of all the cost. That means, where will I store the cost? I have to store the cost somewhere, right? That means I'm keeping an array. For that, I'm using a dynamic array which will store all the possible ways, Whenever you see this word DP will always come whenever you can see that there is all possible ways. Okay, that's how we can keep the track of the minimum cost to reach each and every stone. So what is DP of I? DP of I is nothing but it signifies the at particular instant. Say for example, these are my stones. I'm jumping from this stone to this stone to this stone. At particular instant, I am at this particular stone. So at DP of I means this particular position. What is my cost? So I'm trying to find out the amount of money required to make this particular jump possible. Okay. Now what we will initially do is, we are going to initialize the DP array with 0, the first position, because you know, whenever you are starting to jump, obviously before start you just don't expect to give out money, right? Only when you take a step, only when you move from one step to another, then only you will show some expense, then only you will give away some money, right? So the starting position has to be 0. That's the reason I have mentioned DP of 0 as 0, as no cost is required to be at the first stone. Okay, from here, say for example, this is the person, he is going to jump from this stone to this stone to this stone. So at this particular position, he is not required to pay any money. But whenever he is crossing from this to this or this to this, he is required to pay some money. Like that. Now what we are doing, for each stone I, explore all possible jumps and update the DP of I based on the minimum jumps. So we have to explore all the possible jumps. As I told, what are the possible ways? From here to here, from here to here, from here to there. That means there are a lot of ways, there are a lot of combinations. We can do this with the help of the recurrence relationship, which I am going to explain. Okay. So what you can see is, for each stone I, we can jump to the stone I plus j. That is fine. So see, for example, I am at this stone I. Okay. Now I am at this stone, bigger stone j. So that means I am covering up this particular distance. So I can write I am going to jump I plus j, right? And it is also saying that the jump has to be greater than 1. Obviously, it can be 1 even. It can be just one single jump. But the jump has to be lesser than equals to k. Why k? Because k is given in the question. The particular person can only take k jumps. Means it. Suppose you are at the first position, you can only take 2 steps to reach the second position if the k value is 2. And if the k value is 5, you can take 3 steps, 1 step, 5 steps, but not 6 steps. That means there is a limit. Okay. That's the reason I am saying that j has to be lesser than equals to k. Okay. And I plus j means the total amount of jump has to be lesser than the size of the array. That is also true. Let me explain how. So say for example, this is stone number 1. Okay. This is stone number 2. And this is stone number 3. And this is stone number 4. Okay. That means the size of my array n is 4. Okay. I can take a jump like this, but I cannot take a jump which is greater than 4. I cannot say I will jump from here, 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 everywhere, and my size of the array exceeds. That means it will throw an exception. That means it will throw an exception that you are exiting. That means the boundations will cross. That's the reason I cannot write that. Okay. Now, What is my logic behind finding all possible ways? What is my logic behind finding all possible ways? So this is my main formulas. Make sure you guys try to understand this particular formula. This particular formula is saying that dp of I plus j. What is I plus j? The dp is the I plus j signifies the cost required from jumping from the first stone to the next stone or the last stone. Okay, how much amount of cost is required in one particular jump. So in every particular jump, I'll be signifying the cost. I'll be finding out the cost. So the formula says that we have to take the minimum. Yes, I have already told you. We have to take the minimum of the present jump where I am currently, the jump which I have already done. So I can see this is as my previous or current value. Okay, comma. What I am taking dp of I. dp of I is nothing but my present value, present cost plus absolute value, absolute difference. I'm taking absolute difference of I minus of array of I plus j. That is nothing but this is signifying the difference. This is signifying the absolute difference from one position to another. So this formula is extremely important. Okay. And lastly, what we will be doing is we are going to return dp of n minus 1. Now, your question is, what is n minus 1? N minus 1 is nothing but the last stone, the amount of cost required to reach the last stone. I can write over here the last stone cost. The last stone cost. I'm giving the dollar symbol to signify. Now what we can see is we have to find the time complexities. The time complexity which we will be using is O of n and k. Why n and k? K is the number of jumps and n is the size of the array. We have to iterate through all the possible jumps, that is k, and also iterate from one side of the array to the end. That's the reason we are writing O of nk. The space complexity, since I'll be using and storing everything, the space complexity is O of n, as I'll be storing it inside an array. Okay, now let us understand. Now you will tell me that explain me this particular problem. You have just told me that how this is going to work, but you haven't explained how this formula is actually being applied and how we are getting this particular 30. This 30 is very easy to explain if I am showing you with the help of diagram, but with the help of this formula, it takes some understanding. Okay, so now let us go and try to understand this particular formula in detail. Okay, so what we can see is initially, okay, let us just start from the stone 1. Okay, let us just start from stone 1. So I can write my array as 10, 30, 40, okay, 50 and 20. I have this array and my k value, I can see my k value as 3. Okay, now what it is saying that we have to start at stone 1, which is index 0. Okay, stone 1 means index, so I can write the indices over here 0, 1, 2, 3, 4. Okay, I can write the indices as well. Initially, it is saying that only no cost is required whenever you are at the first position. So I can say, fine, I am at the first position, so I'll put my cost as 0. What about the rest? What about the rest? I can put some really large values, but you will say me why large values? Because remember, what is our goal? Our goal is to find the minimum cost. So whenever we are saying minimum cost, that means we need to have, whenever we are saying minimum cost, that means we need to have an integer.max value stored somewhere. So I can say, I can keep this value as int max. That's the reason I'll be putting integer.max over here, over here, over here. That means every other values right now is at infinity. That means I'm just assuming that they can store very large values. Okay. Now what I'll be saying is dp of 0 is equals to 0. Yes, I've already told the dp of the 0 is equals to 0. Okay, this is my first table done. Now let's see what is there. What is there is, first I can see is my first table has to be filled like this. I have dp of 1 as minimum of infinity comma 0 plus, what is infinity? Infinity, if I see this particular relation, infinity is nothing but I plus j. That means my first jump, from here to here, I'm going here, right? I'm going from the first jump. Remember one thing, from the first stone to the next stone, that means infinity. Okay, I'm taking a step of infinite. That means my current cost is infinite, right? So I'm going to take the minimum of this particular value, infinite comma 0, which is my previous value. Why previous value? As I am in the first stone. This is my first stone. I am currently here. I am going to make a jump. Before making a jump, I was somewhere else. I have to take the smaller value as well. So I'm taking the jump of smaller one. Okay, I'm taking the jump of 0 comma of the position, the cost at my particular position. The cost at my particular position is 10. From 10, I'm making a move till 30. From 10, I'll be making a move till 30, as 30 will be my nearest stone, right? So that is the reason I'm taking a difference of 10 minus 30. Okay, so when I see a difference of 10 minus 30, I'm getting infinity comma 20. So negative infinity, remember this infinity is not large because int max I have taken. Int max taken to minimize the cost. Okay. Whenever I write maximum cost, that time I will write int min. Okay. So that means 20 is my large value. Now let us take another example and let us try to fill this DP table. So 0 is done, 20 is done. Okay. Now let us take, right now I am at 10. Right now I am at 10. But what number of jump I want to take? What is my number of jump I want to take right now? I want to take 2 jumps. That means I want to go from 10 to 40 directly. In this particular case, what is my absolute value? 40 minus 10, which is nothing but 30. I'm getting an absolute value of 30, and my infinity comma 0, my previous value infinity comma 0. What is the minimum of this infinity and 30? 30. So I'll put 30 over here. Okay. This is for starting at stone 1. I can write stone 1 over here as well. Okay. All possible combinations from stone 1. All possible ways I can go from stone wall till the end. Similarly, I am going to do for the rest of the stones as well, right? So let us take the last jump I can make. The last jump I can make is from 10 to 50. Why I can make from 10 to 50? And you will ask me, Arnav, why can't I make from 10 to 20? 20 is my last value, right? No, K value is limited. K value is 3. You can only make up till 3 jumps, right? For our case, we can make up till 3 jumps. That is the reason when I am taking the difference between 50 and 30, 10, I'm getting a cost of 40. So I'm going to update the 40 and keep the infinity as it is. For stone 1, we can just say to the viewers that we have not covered till the end of that particular table, till the end of the particular stone array. Say for example, there are multiple stones present and you have not yet reached the end of the stone. That means you are at you have covered almost all distances, but you have not find a way in order to reach the end of the element from particular position stone 1. Stone 1 is nothing but the 10 position. That means the first stone. Now let us take the example of stone 2. Okay. So before I start with stone 2, I'm going to remove all these irrelevant things. Okay. So that you guys can understand. Okay. Okay. So for stone 2, I'll be doing the same state of actions. Okay. So that you can figure out. Okay. Now stone 2, it is saying that my height is at 30. That means stone 2 is saying that you are right now over here. This particular stone is done. Forget about the particular position 10. Now you are at 30. Now where you have to go? From 30, from where you can go? From 30, if the value as K as 3, that means I can take a step till here. Okay. And how far I can go? I can even take a step till 50. I can even take a step till 50. And I can take a step till the last one as K is 20. Okay. So now if I see all possible ways, 30 minus 40, what I'll be getting is a 10. Okay. What I'll be getting is a 10. But what I can see is 20 is also there. Now you will ask me why this 20, 30, it's so confusing. So let us try to understand it slowly. Okay. So initially, whenever we are at stone 2, what we can see is that right now we are in this particular position. Where our 0 is already covered. Okay, now we have to choose between 20 and our next possible jump, what we can do. So dp of 2 comma dp of 1 plus I minus j. This 30 minus 40, you guys have understand that whenever I am shifting the elements, I am just checking the difference between my next possible move. So between 30 and 40, I'm getting a value of 10. Okay, plus I'm going to add my previously stored value at that particular 30th position, which is 20. So I'm taking 20 plus 10, 30, and my previously stored value is nothing but 30 as well. This value is nothing but 30 as well. So what will I choose? The minimum of 30 comma 30 is nothing but 30, right? Similarly, over here, when I'm going to this particular jump, when I'm going from here to 50, what I can get a minimum jump of 20. I will get a minimum jump of 20 over here. Okay. Plus 20 is also there. 20 is also there. Why? Because initially I already had 20 over there in my position. I already had 20 in there in my position, right? So what I'll be writing is, I can say fine, 40 was my previous value. This 40 was my already present and 20 was my previous. So what I can say is, okay, fine. You are telling me that 40 comma 20 plus 20, which is 40, right? So minimum of all this value is nothing but 40 itself. Okay. So I can easily put 40 over here. What I can do is I can put 40 over here. Lastly, I'm going to make another jump, which is nothing but from this till the end. From the end, what you can see from 30 to end, which is 10. Okay. Now I have a minimum difference as 10. And my previous value was nothing but 20. But what I can see that my initial value was infinity. Yes, because at this position, the first stone couldn't reach. The second stone may have a chance. So between infinity and this 20 plus 10, 30, which is larger, which is minimum, obviously 30. So we are going to take the minimum value. Infinity is a large value and 30 is a small value. We are going to take the minimum of the large of the two, right? So what we are going to take, we are going to put 30. That means stone 2 has moved to all the differences, have moved everywhere. Okay, now let us do the final, but nothing but the stone 3. Stone 3, what stone 3 can do is nothing much, as stone 2 has already covered up all the possibilities, as stone 2 3 has already covered up all the possibilities. So let us try to understand what stone 3 can do. Stone 3 is telling that currently you are nothing but you are at this position. From here, there are only two probabilities. You can either go here, which is from 40 to 50, or you can go till the end, which is from 40 to 20. So in this case, the difference is 10, and in this case, the difference is 20. So you can see the difference is 10 over here, and the difference is 20 over here. 20 plus the previous value 30, 30 is the previous value over here. We can see is nothing but 50, right? So 50 is obviously which value we have to take, the minimum value, the previously covered up distance. We have to take the minimum path. In this way, similarly for 40, and what we can see, a 140 minus 40 minus 50, that is 10, I already told, plus 30 was the previous value, and we are taking 40, and lastly we get a 30. So we can say that stone 3 will nothing but be exactly this particular direction, will exactly be the same as stone 2. Why? Because we are taking the minimum. We are taking the minimum of these two distances, which I have calculated in this particular diagram. This is not required, but this diagram is just for your understanding that how the algorithm doesn't know how many stones are there. Why I say that DP is very important, that right now you are at one position, but say for example the number of stones are 10 to the power of 9. There are so many stones, there is an ocean, and one particular person has to cover up all the stones. Okay, and they can give you a story like that. Then how will dynamic programming be useful? Because in short amount of time it can optimize the cost, because it is exploring all possible ways. It is minimizing the difference between the previously occurred relation, and minimizing the difference. It can also minimize the cost. That's how dynamic programming works in this particular example. Okay, so as you can see, we have the indices. This was the initial array, and our final array has the value 30. 30 is nothing but our last position. So this 30 is nothing but this 30, which is saying that we are really starting from this particular 10 to 20, we will only have a total cost as 30. But as a human, you can understand, because this number of stones is small. Whenever the calculation is small, human beings can figure it out. But imagine there are 100 stones, there are 1,000 stones, and each stone is having 1,000 different type of heights. It is not possible for human brain to compute the number of minimum cost. That's how we are getting the minimum cost over here. Okay, so that was today's problem statement. I hope you guys could understand. If you could understand, make sure you guys like, share, and subscribe by now. I'm just going to quickly put the solution over here. I'm going to quickly put the solution. What I can see, I have made the height, I've taken the size of the array, okay. After taking the size, I am making the DP table. I can say I can making the DP table or cost table, okay. After that, I'm taking my first position of the cost as 0. Rest of the values infinity. I can say infinity. That's the reason I am using integer dot max value. I can also write 10 9. Okay, I can also write 10 10 to the power of 9, which is a large value. Imagining 10 to the power of 9 will not overflow. Next, what I am going, I am traversing through the array I0 and n, and j loop is nothing but checking the number of jumps. Okay, so what I will be checking is, I can write the cost as dp of I plus j is equals to mat.min. I have to take the minimum of two cost, right? So initial cost is nothing but I plus j, right? Comma dp of I plus math dot absolute value, okay, of array of I minus of array of I plus j. Okay, just a second. So I can write, so I'll just have to move this, as this is not visible. So I have just covered up, yeah, I've covered up this. What I can do is returning the last value. I can write the last cost. So I'm getting a 30. But what if I put 10 over here? Let me check whether I get the same answer or not. I'm putting 10 over here. So yeah, because 10 is probably double value, so we cannot take. In case of long values, we can write that. So I'll just keep it to this. I'll compile. Okay. If we have a long data type, we could have used. So value Let us submit this particular solution. You can see this is just 25 line code. 11, this is just 10 line code. But 10 line code, if you want to just copy and paste, you won't understand the dynamic programming, the logic behind it. So make sure you guys like, share, and subscribe to the channel. And it helps me post more amazing contents for you guys. And this was the total approach. I'm just scrolling down a bit so that you guys can see this is the problem statement. This is the diagram which I've drawn for the stones. After that, this is the algorithm followed by the DP recurrence relationship, the time and space complexities, and this is the dry run of that particular problem. Thank you so much. See you in our next video.